Hey everyone, welcome into this lecture on sketching quadric surfaces. You might remember that a quadric surface, from reading your book, is a equation, so it's the graph of an equation in three-dimensional space that has an equation of the following form. So ax squared plus by squared plus cz squared plus dx plus ey, there's a whole lot of parameters here, plus I guess we're up to fz plus EFG, A, B, C, D, E, F, G, that sounds right, equals 0. And so the only criteria here is that at least one, so to make this a quadric surface, quadric means square, quad means square, right? So at least one of A, B, or C has to be non-zero. And that'll give you a quadric surface. If A, B, and C are all 0, then what you end up with is a plane, a linear surface in three-dimensional space. But if any one of these A, B, or C is non-zero, then you have what's called a quadric surface. There are different ways to write these formulas down for these different quadric surfaces. In this lecture, I'd just like to focus on how to sketch a given formula. So we're going to focus on formulas that are kind of nice, so for which these terms at least, the D, E, F terms, have been ignored, and it's always going to be possible to rearrange your quadric surface so that D, E, and F are not explicitly shown, so you can always do some shifting of your coordinate axes to make sure that it's just in terms of A, B, C, and G. So anyway, we'll get back to that later. Here's our first equation. So this is x squared plus y squared equals z squared. We want to try to sketch this surface. This is a quadric surface. So this has, by the way, in terms of the way we just wrote this down, this would be 1x squared plus 1y squared minus 1z squared plus 0 equals 0. All right, so there's our standard form, you might say. Standard form can get a little weird, but here's our coordinate axes. All right, and we want to try to sketch this surface. So one way to do this is to do what we call the tracing method, so the trace method. And the trace method can be done in a number of different ways, but usually we try to take traces that are either equal to the coordinate axes or parallel to the planes determined by the coordinate axes. So our first trace we're going to take, and by the way, we did an example of tracing way back in the lecture for section 12.1 of this section. So you can go back and see an introduction to tracing there as well. But let's say we set z equal to 0. This is going to be a slice or a trace where we are looking just at the xy plane, right? And so if we set z equal to 0 in this equation, we get x squared plus y squared is equal to 0. Well, what's that? Yeah, there's only one point in the plane that satisfies this equation. That's x and y have to both be 0, right? And so at this trace or this slice, we see that there's only one point of our surface at this point, at this slice, right? That doesn't really tell us a whole lot. So what we might want to do next is take a couple of slices that are parallel to this. And what do I mean by that? Well, maybe we take a slice where z is at a height of 1. So what's that? If z is 1, I want to know if we cut parallel to the floor, parallel to the xy plane, if we cut through our surface, what does the shape make? So what kind of shape do we see? And so when z is equal to 1, we plug back into our equation. Now we have x squared plus y squared equals 1 squared. And this is, of course, a unit circle, right? So this is the equation of a circle. And one way that we can visualize this, like I said, is if we were to slice our surface parallel to the floor. So this right here is supposed to be the plane z equals 1. Then in this plane that I've drawn, the graph would intersect and look like a circle, right? And so there's the slice. That's what that would look like. Now we can do the same thing at all kinds of different heights, right? So what if we go up to z equals 2? Then we have x squared plus y squared equals 2 squared. That's a circle of radius 2, right? So what's that? And by the way, centered around the z-axis, right? So that means it's like twice as big. And so we see these slices look like this. We can go down below the floor, below the xy plane. And in this case, we would get x squared plus y squared equals negative 1 squared. But negative 1 squared is just 1 squared. So this slice looks symmetrical to the one up above at a height of positive 1, right? So this is at a height of 2. Down here at negative 1, we get this exact same radius. It's the exact same circle. So you have to pretend the way I'm drawing. All right, but there we go. So we're going to have, as we slice parallel to the floor here, we're going to have a whole bunch of circles stacked up on top of each other, and they're obviously different radii, right? The radius of these circles is different at every step. So what we need to know now is how the heck are we going to connect these, right? So how can we connect these together? And to understand that, we can take slices in a different direction. So for example, we could take a slice when x is 0. When x is 0, we'd be looking in the yz plane, right? Right in the yz plane. So when x is 0, what happens? Our equation becomes 0 squared plus y squared equals z squared, or just y squared equals z squared. What is that? Well, there's a couple different options here, right? So in our yz plane, we have two options. Either z is equal to positive y, then of course their squares will be equal to each other, right? Negative z could be equal to negative y, but then the negatives would cancel, right? Or z could be equal to negative y. So these are two options. And they both obey the equation right here that we're given, that their squares are equal to each other, right? And so what kind of graph is z equals y in the yz plane? Well, it's a line, right? It's a line with slope 1, and it's going to be a line that has to pass through these points, right? These points on the circles, on the respective circles. So there's one line, and then the other one is just a line with slope -1, right? So, and it's got to go through the circles because all these points live on the same surface. Now, we can think about this two different ways. We could do one more slice, right? So we can go to green here, and we can do one more slice where x, we just did x equals 0. We can do y equals 0. And in this case, look what's going to happen. We're going to get the same type of equation, right? If y is 0, we're going to end up with x squared equals z squared. And so in the xz plane, which is, by the way, the plane coming out of the screen and going into the screen, we're going to get these two equations that z equals x or z equals minus x. But that looks just like this, right? So that's two more lines. So these lines are coming out of the screen and going back through back here. And then this one's coming out at us, right? And this one's going back through there. And you can kind of now start to visualize what the shape is going to look like, what the surface is going to look like, because now you can think of just spinning around these lines that all meet at this point. By the way, when a collection of lines meet at a common point, they're called a pencil of lines. It's kind of an interesting name, right? But this pencil of lines, you spin it around, and it's going to trace out what kind of a shape? Yeah, this is going to be a cone. All right, so this is the equation of a cone. So there, by the way, a cone in mathematics always has an upper and a lower half, right? And those two halves are called naps. So this is the upper nap of our cone, and this is another lower nap. There's two naps, and then this is called the vertex of the cone. So the vertex of our cone. And the equation of a cone is, of course, z squared equals x squared plus y squared. And you can then do some shifting in the coordinate axes to move around the vertex, but in general, this is like the standard equation of the cone. What I've drawn here is a circular cone, and then the one that we've studied here is a circular cone. The cross sections are circles. If I were to replace in the equation, if I were to write z squared equals x squared plus y over 3 squared, then this is still a cone, all right, but this is a cone that is stretched in the y direction more than it is in the x direction. So this cone would have an ellipse cross section. All right, it would have an ellipse cross section. It would be much fatter in the y direction. And so the idea here is that this would be like 1 and this would be 3 if in this plane where z equals 1. So that's the slice. But the idea though is that this could be doesn't have to be circles, right? This can be an ellipse. So these are ellipses. All right, so there's an example of how to trace one kind of surface. Let's look at a couple more formulas here. I've got two more formulas for us, and they're very, very similar to this one, by the way. So this was our starting point. X squared plus y squared equals z squared. The next one is going to say, what if you start with x squared plus y squared equals z squared plus 1? Plus 1, all right? And so let's think about how this is going to be different and what's going to happen to it. So it's going to, in some ways, it's going to be very similar, right? That's kind of the point here. It's going to be very similar in some ways. Here's our x, y, z. We want to try to trace this. By the way, when we draw these pictures, we're not expecting them to be perfect, right? We're just trying to get a good feel for what our shape looks like. So let's take some traces again, right? So this time, if we take our trace where z is equal to 0, now our equation becomes x squared plus y squared equals 0 squared plus 1, right? Equals 1 now. So instead of having just a vertex here, just a point, now we're going to have a unit circle. We're going to have a unit circle in the xy plane. So our unit circle, right, lives right there. So there we go. So there's the slice of this thing that happens in the xy plane. All right, let's take another slice. Let's move up. Let's move up to z equals 1. Same kind of idea that we used before, right? So as z goes up to 1, what do we have now? We have x squared plus y squared equals 1 squared plus 1. That's 2, right? And so this is a circle whose radius is square root of 2. The radius is the square root of this number, right? So that's a little bit bigger than 1. It's not growing quite as quickly as the one in the last example, but that's okay. But the point is that it's a circle that's now a little bit wider, right? Has a larger radius, I should say, than the previous one. And by symmetry, because everything's squared here, by symmetry, anything that we do to positive z's is going to look exactly the same below the floor, right? So that has the same equation, except that's being sliced down here at negative 1. So I'm going to try to draw this to have pretty much the same shape as the one above. So now we've got circles over circles. They're getting fatter down below, fatter up above, right? When they go through the plane z equals 0, so the xy plane. That's the plane where they kind of all come together. And now the question again, once again, just like it was before, is what happens? How do we connect these, right? So are we going to just draw straight lines again and they come to like a point around the waist here, or is something else happening? So let's once again take our slice when y is equal to 0. All right. If y is equal to 0, now our equation says that I think I want to take x equal to 0 first. I like to work in the yz plane because it's the one that's the plane of the screen. So let's take x equal to 0. That'll be the yz plane of the screen. Now our equation is going to say what? Y squared equals z squared plus 1. All right, and if we rearrange this, we can write this as y squared minus z squared equals 1. And so this looks like the equation of what? Yeah, this is a hyperbola, right? So this is a hyperbola. So that's a hyperbola. And the hyperbola passes through, so when z is 0, y has to be 1, right? And then it works its way out from there. So obviously, y can't be 0. There's no way for negative z squared to equal positive 1, right? So z has to work its way out to 1. So there we go. There's our point. And then this thing opens out like this. So imagine we have these points here. And then the same thing on this side. So, right. And this one's going to come around. It's not the most symmetric looking thing, but this is the idea. And if we were to take the same slice, right, the same kind of slice in the xz plane, we're going to get the same picture again, right? So this is exactly, if we take y equals 0, now we're going to have x squared equals z squared plus 1. Same exact equation. X squared minus z squared equals 1. That's a hyperbola. This one goes back that way, comes out of the screen. Oh boy, very bad. It's got to go through there. Right? Looks something like this. And the idea now, again, our pictures, our drawings are not expected to be perfect, right? But the idea is that as you spin this around again, you're going to be able to see the shape that's being traced out, right? So it's going to be kind of the shape of like a nuclear power reactor somehow, or some very special gear of some kind of machine. So there's the idea here. It's very symmetric. It's supposed to be rotationally symmetric. And so this is the shape, right? And it's hollow. It's hollow. You can look right through it. If you were able to tip this up, you could look right through it. And again, our cross sections are circles. If we had changed our coefficients on the x squared or y squared, we would get ellipses here, ellipses, instead of circles. So that part makes a lot of sense, right? And we need to classify this. So we need to give this thing a name. So this thing in two of the cross sections, so the blue and the green cross sections, we've got the same shape in both of them, right? And that shape is a hyperbola. So hyperbola happened twice. All right, you might remember from that first lecture video of section 12.1 we built a paraboloid where we had two directions that were parabolas. This time we have two directions that are hyperbolas, and then in between we have these circles, right? Now, we need to be very careful how we describe this, though. This surface is all one piece, right? You could walk around and never leave this surface and get to any point on the surface. So this thing's actually called a hyperboloid of one sheet. So it has just one connected sheet. All right, and so there we go. Let's now take a look at one more example, and it's going to have a name that's very similar to this, but it's going to be different. So here we go. X squared plus y squared equals z squared minus 1. You probably could have guessed that that's what I was going to do. So we had x squared plus y squared equals z squared. We added 1. Now we're going to try subtracting 1. What's the difference going to be, right? What's going to happen here? So let's follow the same kind of order of operations that we've been doing. Take this slice where z is equal to 0. Now, when we set z equal to 0, look what happens. We have x squared plus y squared equals negative 1. Can this happen? No. This is shenanigans, right? So that means there is no portion of our surface, if we were to slice along the floor, right, the xy plane, we would not intersect with our surface. Our surface does not have any points that lie at that height of z equals 0. All right, and now we start to look at this. Well, what's the problem, right? Our circle can't have a negative radius. If it's added together here, you can't have a negative radius over here, right? And so what do we have to do? Well, we have to think about for what z values does this start to be positive, right? So z squared minus 1, we want to be at least greater than or equal to 0. So that means that z squared has to be greater than or equal to 1, right? And so in general, our absolute value of z has to be greater than or equal to 1. And so this means that our graph doesn't even start until we get up to a height of 1 or down to a height of negative 1. All right, so let's take those two slices. Nothing in between, right? Nothing in between, because then we'll have a negative radius on the right-hand side. So let's take z equal 1 and see what happens. Here we have x squared plus y squared equals 1 squared minus 1. That's 0. So actually, we just get this point, right? This is similar to our cone. We just get this point, and by symmetry, we just get this point down here. Let's go up a little bit higher, right? So let's take our slice as z equals 2. So this time we have x squared plus y squared equals 2 squared minus 1, which is of course 3, right? So this is now a circle with a radius of square root of 3. But the point is that it's a circle, right? So now we've got this cross section. That's at a height of 2. And again, by symmetry, down here at negative 2, we'll have a circle with the same radius, pretend, all right? And again, nothing in between this negative 1 and this 1. All right, well, we need to know how the heck are these going to be connected, right? How is everything going to come together? So let's take our slice then where, x equals 0. Take our yz plane, and let's see what happens. Now we have y squared equals z squared minus 1. All right, if we get everything on the same side, y squared minus z squared equals negative 1. And then if you multiply through by a negative 1, you could write this as z squared minus y squared equals positive 1. This is our old friend the hyperbola, right, from the last example. But this time it's going to open upward in the z direction and downward in the z direction, and it's going to then spread in the y. So in other words, it's tipped from the one that we drew in the last example, right? So it's actually looks something like this. The way I've drawn it here is very steep looking, and it's supposed to be symmetric, but it opens this way. So there's our hyperbola in the yz plane. You can imagine in the x z plane, it's going to look the same, right? So y equals 0. It's all symmetric here, right? So this is going to give us now x squared equals z squared minus 1. And rearranging, we'll have z squared minus x squared equals 1. And this is now going to be a hyperbola that comes out of the screen and goes back like this. And comes out in the forward direction, goes back like this. And so now you can see that what we've got is a surface that actually has two completely distinct components, right? So just again, by spinning around using our symmetry, we've got like a bowl type shape up on top, right? And then another one. So this is all part of the same surface. This is all part of the same surface down here, right? So, and in between, this is where our radius doesn't happen, right? So this is our z values between negative 1 and 1. And these things obviously continue on forever, right? It's infinite surface. Continues on forever. this thing, again, has two cross sections that are hyperboloids, but this time it's cut into two sheets. So you can imagine if the last one was called a hyperboloid of one sheet, we can classify this one as a hyperboloid of two sheets. All right, and so this one comes from subtracting the number from the z squared on this side. On this side, again, you have you can make these ellipses instead of circles just by adding coefficients to the x or the y, and or the y, either one. And in general, you can always rearrange your hyperboloids to be in either one of these forms. So some variable squared plus the other variable squared equals the third variable squared plus or minus a number. And the plus or the minus, that portion determines whether it's one sheet or two sheets. So the minus on this side is two sheets, and the plus on this side is one sheet. If you can get it so that it has nothing on the right hand side, then you get a cone. So the cone is like the link between the hyperboloid of one sheet and the hyperboloid of two sheets. And yeah, that's how these things all fit together.